A quick note before we dig into the meat of this chunk of material. I just want to notice something about matrices inequality and the matrix vector product. And what I want to note is that two matrices of the same size are equal if and only if the matrix vector products AV and AB are equal to each other for every V. So what I'm saying is that AV has to be equal to BV for all V in capital V. Or I guess what I mean here isn't capital V. I guess I mean Rn, right? For these products to be defined, the vector has to have n entries. So this should be Rn here. All right, so on the one hand, one of these is obvious. This direction is obvious because if you have equal matrices, then of course these matrix vector products are the same because this side is literally A times V because B is equal to A. So this direction is obvious. It's the other direction that's tricky. So to see why this is true, first let's write A in terms of its columns. So let's say its columns are A1, A2, and so on down to A. There's going to be n of them because it's m by n, so there are n columns. And let's do the same thing with B. So B, let's write it in terms of its columns, B1 down to Bn. Okay. These vertical lines, I'm not implying that somehow these are augmented matrices representing a system. I'm just separating the columns, the symbols that I'm using for each column. Okay, so now remember, for this part, we're assuming that all of these matrix vector products are equal for every choice of vector v, and we want to show that these matrices are equal. Okay, so this equation, since it's true for every choice, since it's true for every choice of v, in particular, it's true for this v, the vector in Rn that has a 1 in the first entry and a 0 in all the other entries. So what is A times this vector? Well, first of all, before we actually calculate it, notice that we're assuming that it's equal to B times the same vector. Okay, so let's work out this vector product. Well, this vector matrix product, how do you do a matrix vector multiplication? Remember, you turn the vector, you kind of turn it sideways above the matrix, and then sort of sweep downwards. Well, as you do this, right, since most of these are all 0, the only products that you get that are non-zero are the ones that give you the entries in A1. So this product is actually just the single column A1 as a column vector with m entries. Well, the same thing goes for B, right? When you do this matrix vector product, the zeros sort of kill off all the contribution from the other columns, and you just get the first column. And so you get a single column whose entries are the same as the first column of the matrix B. But looking at this chain of equalities, this means that A1 is equal to B1. So these matrices actually have the same first column. Well, you can see now what's coming. Do this with the next standard basis vector in Rn, A times the next standard basis vector with a 1 in the second entry. On the one hand, it has to be equal. By assumption, we're assuming it's equal to the B times the second standard basis vector. But A times this vector is just the second column of A. B times this vector is the second column of B. And so these columns have to be equal. And so on, right? This is going to be true for every standard basis vector. So I think the symbols that we were using for our standard basis vectors were EI. So A times EI has to be equal to B times EI. That's by assumption. But this calculation, right, EI is the vector that has a 1 in the ith entry. So when you do this product, you're right, the pattern of this calculation holds, and you get A sub I, the ith column of A, but this product is the ith column of B, and then this chain of equalities shows you that these two are the same. So if we go back up to A and B, all of their columns are equal, and so A is actually exactly the same matrix as B. So we can check if two matrices are equal, not necessarily by looking at their entries. We can actually instead just think about what happens when you multiply them by vectors.